Students, I welcome you in today's class of physics. As you all know, we were discussing a topic, refraction of light at a plane interface, total internal reflection, optical fiber. I hope you know very well, in the previous two lectures we had covered out most of the topics of this chapter. So now today's class we will discuss about the critical angles. Fine. So let's move. Here you can see this is the topic, critical angle and total internal reflection. Clear? So now what is the critical angle? When a light ray passes from a denser medium to a rarer medium, say of glass to air. Clear? Suppose our denser medium is glass and air is the rarer medium. So what happens with the light? It bends away from the normal at interface of the two media. That is, the angle of refraction is greater than the angle of incidence. Fine. Here you can see in the figure number 8, there are the three figures, figure 1, figure 2 and the figure 3. Clear? On increasing the angle of incidence, the angle of refraction increases. This is the Snell's law. As you know very well, in the previous lectures we were discussed about the Snell's law. Clear? And for a particular light, angle of incidence C, the angle of refraction become how much? 90 degree. Clear? This is the important thing that is written here. That is, the refracted ray grazes along the interface. Fine. Here you can see this is the figure number B in that case. This angle of incidence C is called the critical angle for the interface. Thus, we can say that the critical angle for the two given media is the angle of incidence in the denser medium, for which the angle of refraction in the rarer medium is equals to how much? 90 degree. This is the definition of the critical angle. I hope it is clear. Its value depends upon the nature of the two media and the color of light. Fine. So for glass air interface, the critical angle for the visible mean light is about how much? Is about 42 degree. Now we will talk about what is total internal reflection. This is the total internal reflection. When the angle of incidence in the denser medium is increased even very slightly beyond the critical angle. I hope you know very well the critical angle, 90 degree. So if we slightly increase the angle of incidence in the denser medium beyond the critical angle, what will happen? Then the ray of light is reflected back completely into the denser medium. It means that it does not change the medium. Fine. So it's completely reflected back into the same medium in accordance to the law of reflection. This is the figure. See, here you can see this is showing the total internal reflection. This one. This is called the total internal reflection. Total because the whole of the light is reflected back into the denser medium. Here you can see the angle of incidence is greater than the critical angle. So the whole of the light does not change the medium in figure C. So we can conclude here that when a light ray traveling from a denser medium to a rarer medium, clear, is incident at the interface of the two medium, the angle greater than the critical angle for the two media, the ray is totally reflected back into the denser medium. This is the definition of the total internal reflection. Clear? Thus now we are considering the two conditions to be fulfilled for the total internal reflection. In examination there might be asked what are the two conditions or necessary conditions for the total internal reflection. So you have to write down these two conditions. What the conditions is? The first one is the ray incident on the interface of the two media should travel in which medium? In the denser medium. Clear? Now what the second one? The angle of incidence should be greater than the critical angle for the two media. These are the two conditions you have to keep in mind. Now what is the relation between refractive index and critical angle? This one. Relation between refractive index and critical angle. Suppose if the rarer medium be represented by 1 and the denser medium by 2, then by the Snell's law, the refractive index of the rarer medium with respect to the denser medium is given by this, like this, 2 and 1 is equals to sin C upon sin 90 degree. So how will we get how much we get here, sin c, because sin 90 equals to 1. But in place of 2 and 1 we can also write this 1 upon 1 and 2, where 1 and 2 is the refractive index of the denser medium with respect to the rarer medium. Clear? So there is a relation set up between 1 and 2 and sin c equals to how much, 1 upon 1 and 2 equals to sin c, or you can also write like this, 1 and 2 is equals to 1 upon sin c. Clear? For example, the refractive index of glass related to air is equals to A and G is equals to 1 upon sin C, where C is the critical angle of the glass air interface. Now, since refractive index depend upon the wavelength of light, fine. So, the critical angle for a given pair of media is different for different wavelength color of light. This is the thing. The expression for the critical angle also be written in terms of the velocity of light in the two media of the interface. For example, the critical angle for the glass air interface can be written like this, sin c is equals to 1 upon A and G, that is velocity of light in glass to the velocity of light in air. Now, what are the importance of critical angle and application of total internal reflection? These are the some importance. This one. Mirage. I hope you know what is mirage. It is an optical illusion occurring in deserts, on a cold tarred roads, on hot summer days. Clear? When you travel goes on the road in the summer, you see there is a very shiny. So when you at a distance, if you see the road, there it looks like a very shiny, or it seems like to be a water spread over the surface of the road. Fine. This is due to the mirage. Now, what is mirage? Is an object such as tree appears inverted to a distant observer who gets the wrong impression of a pool of water in which the tree is reflected. You can see here an observer seeing an inverted image of the tree is due to the mirage. This illusion is called the mirage, which occur due to the, and mirage happen due to the total internal reflection of light. Similarly, in summer the sand or the road surface become very hot due to the intense heat of sun rays. Fine. Therefore, the air layer close to the surface of the earth become hotter and hence rarer, while the higher layers are colder and hence denser. Thus, an oblique ray of light from point O, you can see here at point O, this one, on a tree travel from denser to the rarer of the atmospheric air and bends away from the normal. Clear? According, the angle of incidence goes on increasing and ultimately exceeds the critical angle at certain layer. The ray is then totally reflected and travels upward. Fine. Therefore, denser layer bending more and more towards the normal when it reaches the observer eyes. It appears to come from the point I. Hence, the observer see an inverted image of the tree as though reflected from the pool of water. You can see here, this is the reflected image of tree there. Fine. Now, there is another example, brilliancy of diamond. The brilliancy of a diamond is due to its small critical angle with respect to the air. The refractive index is how much? 2.42, and the critical angle is about 24 degree. Fine. The light which enters the diamond is completely reflected, repeated at various faces of the diamond, and emerges only when the angle of incidence at some face is less than 24 degree. Thus, all the light entering the diamond emerges in a new direction only, and the diamond sparkles brilliantly when seen along this direction. I hope you understand it. Now, the third one is the totally reflecting prism. Right angle isosceles glass prism are frequently used as a reflectors of light in optical instrument. Why? Because of their several advantages. They are known as totally reflecting prism. There are three methods of using prism as a reflector. Now, what are the three methods? We will discuss. First one is as a simple reflecting prism. So, you can see here in this figure, When a ray of light enter normally at one of the shorter faces of a 45 to 90 degree to 45 degree crown glass prism, it strikes the glass air hypotenuse interface at an angle of incidence of how much? 45 degree. You can see in the figure number 10, this one. Clear? Since this is greater than the critical angle for glass air interface, which is about how much? 42 degree. As I already told you in the above lines, the angle of glass air interface is how much? 42 degree. So the ray is totally reflected and emerges normally through the second shorter face of the prism. Thus the ray is turned through 90 degrees. Such prisms are used instead of plane mirror in periscopes. The second one is as a reversing prism. Clear? Here you can see the second one is your reversing prism. When a light ray enter the right angle isosceles prism normally at the hypotenuse face, you can see here this figure, it is totally reflected at each of the shorter faces and it turns and emerges anti-parallel to the original directions. Thus it is turned out through how much angle? 180 degree angle. The figure also shows the reversal of image due to reflection by the prism. A pair of such prism is used to reverse and erect the image in binoculars. Now we will move to the third one as an erecting prism. Clear? A method of producing erection of image by a reflecting prism. So deviating the light ray shown in the figure number 12 here. You can see this is an erecting prism. In this case, the light ray is first refracted at a shorter face, then totally reflected at the hypotenuse face and finally emerges through the second shorter face parallel to its original direction. The image is however turned upside down. Such a prism is used in projection lantern to produce an erect image of an upside object on a screen. The first image produced by the lantern is inverted. Totally reflective prism has the following advantage over the plane mirrors. These are the some advantage of totally reflecting prism over plane mirror. The first one is reflection occurs at one surface only and so there are no multiple images. This is the first advantage. The second one is nearly 100% of the light is reflected against about 80% for a silver glass mirror. Third one, there is no silvering to tarnish of or wear off. The fourth one is there is almost no change for the prism to become bent or distorted. Clear? Hence high quality image is produced. However, prisms are costlier than the mirror of equal size. Now we will talk about optical fiber. What is optical fiber and what are the uses of optical fiber nowadays? So an optical fiber is a device which transmits light introduced at one end to the opposite end with a little loss of light. Clear? You can see you are using the internet connections because of due to the optical fibers. So this is the figure of the optical fiber. It is based on the principle of total internal reflection. It is based upon the principle of total internal reflection of light. You can see the construction also here in figure number 13. An optical fiber consists of a cylindrical central core, clear, whose diameter of the order of few micrometers, made of thousands of long and extremely thin strands of high quality glass or quartz. The core is clad by material of slightly lower refractive index. So you have to know or remember that the refractive index of the core is slightly lower than the cladding. What is the cladding? Cladding is a layer over the core to make it safe. Fine. Light of propagation. Now how light is propagated into the optical fiber? So when a light is incident at a small angle at one end of the optical fiber, it gets refracted into the core and incident on the core cladding interface. Here you can see in the figure number 4 the transmission of light. If the angle of incidence and the interface is greater than the critical angle, then the ray undergo total internal reflection. Fine. At the interface. Further, because of the cylindrical symmetry in the fiber structure, this ray suffers total internal reflection at the lower interface also and is guided through the core by repeated total internal reflection and finally comes to out of the optical fiber or bent or twisted fiber. Light guidance can occur through multiple total internal reflection. Fine. In the figure number 4 you can see this. This is the figure. What are the applications of optical fiber? If we talk about, so optical fiber have many applications in optical and medical fields. First one, a bundle of optical fiber is called a light pipe. You can see here. It can transmit the image of an object to a very large distance. This is the most important advantage of optical fiber. Because the light pipe is flexible and can be twisted in any manner, it can be used in medical and optical examinations, often the inaccessible parts of human body or an equipment. Clear? You know the medical term endoscopy. Fine. So in endoscopy we are using the optical fiber. Clear? For example, a physician can see the interior of the stomach of a patient by running two light pipes down the patient's throat. Fine. So light enters the stomach through the one pipe and illuminates the interior of the stomach. So some of the light reflected from the interior comes back through the second pipe and they form an image on the monitor screen of the physician to see. This is called the endoscopy. That is the thing I am talking about, endoscopy. Now the second one is the optical fiber are used for transmitting and receiving electrical signal by converting them into light signal by suitable devices. Fine. Now the last point and the third one is they are used in telephone and other transmitting cables. Each fiber can carry as many as 2000 telephone conversation without much loss of intensity. So this is the end of the chapter, students. I hope what I taught you are totally understandable and know each concept properly. Fine. So that's all for the today's class, student. We will meet in the next class with a new chapter. Till that, proper do study. Thank you, class. Thank you.